We will look at sequences today. A sequence is a function whose domain is the set of positive integers. Positive integers. 1, 2, 3, 4, 5, 6, 7, 8. That's the domain. So it's not a continuous function, meaning we don't have like 1.1. We could not connect all these dots. They would just be dots if we were to plot them. So let's just kind of take an easy example. Given the function f of n, not an x, but f of n equals 1 over n plus 1, evaluate that function. So f of 1 would be 1 over 1 plus 1, which is 1/2. F of 2, so just very easy plugging in numbers. And you could probably see the pattern and then just write down the answers. In fact, this chapter is going to be about numbers and their patterns. Our domain, again, is just the set of positive integers, not negative, not fractions, not decimals. A sequence is really just a list. Now let's look at some different notation called nth term notation. So we have a set, that's the braces, of d sub n, and it's defined as -1 to the n minus 1 times n over 2n minus 1. Find the first 4 terms. Well, remember, the first 4 terms always going to be n is 1, 2, 3, 4. So if it's first 5 terms, 1, 2, 3, 4, 5. It always starts with 1 and increases by 1. So let's just look at our formula. So we have the first term, this d sub n is going to be 1. We're going to use those subscripts, equals -1, 1 minus 1, 1 over 2 times 1. What's going to happen with this exponent? That's going to be 0. Anything to the 0 power base raised to the 0 power is +1, so that's going to be +1, and that's going to be 1 over 1, which is 1. So the first term is 1. What about the second term? Again, everywhere there's an n, we're putting in a 2. So that's going to be -1 to the first power. That's going to be 2 over 3, which is -2/3. So our first term was positive, our second term was negative. What about our third term? That's going to be to the second power. A negative raised to an even power is positive, so that's +1 over 3/5. So our next term is positive. Let's just do the last one. That exponent's now odd, so we have negative over 4/7. Now the reason why I did this example is because of that exponent. When you have -1 raised to a power, and those powers are going to change by 1, it's going to make the series, it's going to make the sequence alternate, as in positive, negative, positive, negative. It may actually start negative and then go positive, but it alternates between signs because of that part of the function. Now the next examples we're going to go through, and they actually want us to find a formula for the nth term. So it says, look at this and see if we can write a function of n. Well, we know we have a fraction. Does the numerator change? No, so that's going to be 1. It's the denominator. Now remember, n is 1, then n is 2, then n is 3. So look at those first numbers. 1, 2, 3, 4, keeps going. That's n. Then it's being multiplied by, well, 2. What's 2 in terms of n? Well, if n is 1, wouldn't that be +1? Convince yourself, if you plugged in n, would you get back those terms? Well, let's see. When n is 4, wouldn't that be 4 and 5, which would be that one? So just kind of weird looking. Let's look at this next one, a little bit harder. Well, we have even numbers, and they alternate in signs. Well, we just saw something like that. So I know I need a -1 to some power. multiplied by something. So that negative is going to take care of the sign. So 2, 4, 6, 8, 10, keep going. Well, n always starts with 1. So could I do n plus 1? Would that work? Well, for n is 1, I'd get 2. But what happens when n is 2? I'd get 3. So that wouldn't work. So let's erase. Try again. What can we do to get multiples of 2? Could we multiply n times 2? When n is 1, I'd get 2. When n is 2, I would get 4. When n is 3, I'd get 6, and that would work. Now, what about the exponent? Alright, well, if n is 1, that's going to give me negative. So I could add 1 or subtract 1, and that's going to make it start out to be positive. So again, if you have an alternating sign, you need a negative 1 to the n power, to the n plus 1, or the n minus 1. Really, those are usually the same. You just have to see where your starting point is. And yes, this is some guessing. Alright, let's look at this third one. Again, I have a fraction. Let's look at those numerators. Am I multiplying by 2? No. Are they multiples of 2? No, but I am multiplying by, well, let's see, 2 times 4 is 2, times 2 is 8, times 2 is 16, but that's different than there, so I know it's not 2n. What could it be? Well, it's powers of 2, isn't it? What about 2 to the n power? 2 to the first, 2 to the second, 2 cubed, 2 to the fourth. I think that works. What about the denominator? 3, 3 squared, 3 cubed, 3 to the fourth. Ah, those are powers of 3. So I could write it like this or that. Again, this chapter is a lot about patterns and recognizing those patterns. Now we're going to look at what's called recursive formulas. Most famous of those is the Fibonacci sequence. Do some research. But a recursive formula says you have to have previous terms to get to the next one. The Fibonacci sequence says add those and get the next term, which is 2. Then add the 2 previous and get the next one. Add these, and so forth. So a recursive formula uses the previous terms to get the next terms. So on this one, they tell us the first term is 3, and the subsequent terms are in terms of the previous one. I know that looks weird, so we know A1. Let's find the next 3 terms. So A2, using this formula, wherever there's an n, I'm going to put a 2. So 4 minus A, 2 minus 1. What does that mean? That's the first term. Do I know what the first term is? Yes, I do. It's 3. So the second term, I had to know the one before it. Alright, so the third term is 4 minus A to the 3 minus 1. So that's the second term. Well, what is the second term? What I found in my previous answer. And it's 3. So the second term was 1. The third term is 3. What about that fourth term? Alright, there is the previous term. So we have 4 minus 3, and we're back to 1. That's kind of weird, but it does happen. So those are the next 3 terms. Again, a recursive formula is always in terms of a previous term. Let's do this one. So the first term is negative 2, and I have that formula. So the second term is n, which in this case is 2, plus 3 times A to the 2 minus 1. That means the first term. Well, what was the first term? Negative 2. So what is that? Negative 4. Third term. We have n, which is 3, plus 3 times the previous term. I'm going to skip a step here. The previous term. So that was the second term. And what was the previous one? It was negative 4. So we have negative 12 plus 3 is negative 9. The next term would be 4 plus 3 times the previous term. In this case was negative 9, so we have negative 27 plus 4, I think, is negative 23. My challenge is, can you find a formula for the Fibonacci sequence? Meaning, can you write it something like that knowing you have the first term? Or Google it. Read about the Fibonacci sequence. Next thing we're going to look at is what's called sigma notation. Sigma is a Greek letter, and this is the capital sigma, and it means to have the sum or to add up all the terms. So let's see, what is that going to do? So we have this is called the index. So it's like our n values or our domain. Or if you've ever written a computer program where you had a loop and you had to have a counter, this is the counter. So it says let k equal to 1 and keep going to 5. And remember, they're just whole numbers. So this is going to be when k is 1, when k is 2, 3, 4, and 5. Where did those plus signs come from? That sigma says to add them up. So let's do that. So I have negative 1 plus 0, 1 plus 2 plus 3. 5. Pretty easy. Right here, I'm going to go to n. Well, isn't that forever? Ooh, what is that? So that would be like 1 plus 1 squared plus 2 plus 1 squared plus 3 plus 1 squared, and I would keep going until I had n plus 1 squared. So I physically cannot add all that up, but that's what that means if you were to expand it. So could we go backwards? Can we have this sum and see if we can write it in sigma notation? This is kind of like finding the formula, if you will. So the sigma comes from the pluses. I always like to start, and let's just use n. I like to start it at 1. The question is how far did I go? And I have to get the odd numbers. The odd numbers. Now the even numbers, remember 2, 4, 6, 8, keep going. We had 2n. So the odd numbers, wouldn't that be 1 off? So what if I subtracted 1? Would that work? Let's see, if I put in 1 for n, what would I get? That would be 1, okay. And then if I put in 2 for n, let's see, that would be 4 minus 1, and that's 3. I think that's okay. So I think this is a good formula, but how far do I need to go? Let's see, 2, and then I would go to 3, and I would get 5. So how far would I go here? Well, 12. So I would stop at 12. So that's the answer. Write the following sum using sigma notation. Again, it's kind of weird. Okay, so let's do this one. This last part really helps us out. Kind of helps us with that formula, don't you think? I have to first look at that negative because it does alternate signs, plus, minus, plus, minus. So I know I need a negative 1. I might need it to the n power or n plus 1. So if that's to the first power, I would get a negative. So how about plus 1? I think that would be good. And then 2 over 3 to just the n. Remember, 2 to the n would be 2, 4, 8, 16. We did that one up above. But look, here's 12, here's 11. So what is n going to go to? It's going to go to 11 because 11 plus 1 is that 12. Expand it out, convince yourself that indeed you would get what you started out with. That's sigma notation. We'll be using that in the next few lessons.